All right, we're going to talk about the derivative as a rate of change. So an instantaneous rate of change. So f of x, or f prime of x sub 0 equals the limit as h goes to 0 of f of x sub 0 plus h minus f of x sub 0 all over h. This is the instantaneous rate of change. You might have remembered this and go, oh, hey, that looks really similar to the slope of the tangent at a point. Absolutely, because it is the derivative, okay? So we want to kind of understand that the derivative gives us a function for instantaneous change. And then what we're going to do is to find the instantaneous rate at a specific point. We just plug that point in. So our example 1 is, how fast does the area change with respect to diameter when the diameter equals 10? Okay, so here's my area formula. And so what's going to happen is I'm going to find the derivative of this. So a prime is going to be pi force times 2 d. Okay, so that's going to give me pi halves d. Okay, then it says, well, that's my whole function there. So I took the derivative of this with regards to the diameter. And then it says, well, what is that actually when 10 goes in there? So now I have pi halves times 10, which is 5 pi, okay? So that's how quick it's going to changing. You could, plug that in your calculator, get a decimal equivalent, but that's fine. So the velocity is the derivative of a position with respect to time. So if I have my position value there, I can take the derivative and find the velocity of it. If a body's position at time t is s equals f of t, then the velocity is, velocity p is derivative of the s function over time, which equals the limit as the delta t goes to 0, f of t plus delta t minus f of t over delta t. Notice that these are essentially the same thing, except that I have not plugged in a value for t yet. Okay? So we're going to kind of go over an example of that. I've already written it all up here to kind of give you an idea here. So how is velocity different than speed? Okay, well, velocity has orientation. So it's going to be positive and negative depending on your perspective. So if I look forward and I walk forward, I'm going to have a positive velocity because my perspective is here. So if I look forward and I move opposite the direction I'm looking, then I'd have a negative velocity. Okay, so understand that velocity is just in respect there. Speed is the absolute value of the velocity. So speed, we don't care about the direction it's traveling. We only care how fast it's going. So it's the absolute value of it. And the acceleration of a body is the derivative of the velocity, or it's the second derivative of our position function, okay? And then there's this idea of jerk. The jerk is the derivative of the acceleration, or it's the third derivative of the position function. So we're going to look at one of these examples here. So it says basically the example is a rock is blasted straight up, okay? And it follows this positional path. S equals 160t minus 16t squared. So this is kind of the diagram of what happens. So what happens here is I have a rock. I'm going to put some dynamite underneath it. I'm going to blast it straight up. Okay, it's going to come here. It's going to be at 256 here height. There's going to be at some point where it's at the maximum height. Okay, I may not know what time that is or what that height is. I'm going to find it. But understand that at my max height, this rock's going to come up. It's going to have a 0 velocity for that instant there. And then it's going to start falling down. And it's going to drop back down to 256. And then eventually back down to 0. Okay? So we want to have to understand that this concept of once it gets up to the very peak up there, it's going to be suspended for a split second where there is no velocity. Okay? Until gravity takes a hold again and pulls it down. Okay, so our function is s equals 160t minus 16t squared. A is how high does the rock go. B is what is the velocity when the rock is 256 256 feet above the ground. Remember, there's two times when it happens, when it's going up and when it's coming back down. What is the acceleration function? And then when does it hit the ground? So those are the four things we're looking at, okay? So yes, in algebra, you could actually find the vertex formula from this, plug that in, find the height. We're in Calc, so we're going to kind of use the Calc method. So the idea is that we understand that the velocity is 0. So what I'm going to do is I'm going to have my distance function here of 160t minus 16t squared. What I'm going to do is I'm going to take the derivative. Okay? The derivative of that is 160 minus 32t, right? Bring my powers down. And then I'm going to set that equal to 0 because I know my velocity has to be 0. So when I solve this out, I get t equals 5. Okay? Could I have done the same thing here? Okay, negative b over 2a, 160. Yes, it gives me the same thing. I'm going to take that 5, plug it in, so I get my position here of 160 times 5 minus 16 times 5 squared. So I get 800 minus 400, or 400 feet. Okay, so this rock is going to be blasted 400 feet into the air. So part A is 400 feet. Part B says, what is the velocity when the rock is 256 feet above the ground? Well, I need to know at what time that's going to occur. So I'm going to set this equal to 256 because that's my height. So I need my 2 times. So I'm going to solve this. So what happens here is I'm going to get this all on the same side. I'm going to divide everything by 16 because everything's divisible by 16. So it simplifies it into t squared minus 10t plus 16 equals 0. That factors into t minus 8 and t minus 2. So my 2 times are 2 and 8. So I know that here my time is 2 seconds going up and a total of 8 seconds back over. Okay? Now that doesn't tell me my velocity. So now I need to take my velocity function here and plug in 2. So 160 minus 32 times 2. 160 minus 64, or 96 feet per second going up. So it's 96 feet per second going up. I plug in 8. I have 160 minus 32 times 8 equals 160 minus 256, which is negative 96 coming back down, which should make sense, right? So positive value is going up, right? I'm looking at how fast is it traveling up. Coming back down, it's going to have a negative velocity. Okay, and it should make sense that they are the same because remember, parabolas are symmetric. Okay, C says our acceleration. So what we're going to do is we're going to take the derivative of our velocity function here. Well, the derivative of 160 is 0. The derivative of negative 32t is negative 32. There's our acceleration function. Okay, so our acceleration function is negative 32 feet per second. And then the last thing is it says, well, when does it hit the ground? Well, that's basically taking my quadratic equation, setting it equal to 0 and solving. So I'm going to factor this. Excuse me. I have 16t equals 10 minus t. Well, this one's 0, which makes sense, right? It starts on the ground. Makes sense. This is going to be 10 seconds. So at 10 seconds, that's the duration of the flight, okay? Probably could have gotten that knowing that this goes up to 5, took 5 seconds to reach up here, kind of 5 seconds back down, or this is 2 to here, this is total distance is 8, 2 to there, okay? So understanding that the derivative is giving us an instantaneous rate of change, okay? The derivative of the derivative is giving us instantaneous acceleration, okay? And those are going to be used throughout. Those people that are in physics, you see this all the time. You guys utilize this constantly, okay?